Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. A self-published pamphlet, a mere 6 pages of densely packed mathematics, began to circulate in the intellectual centers of Europe around 1824. Its author was an unknown Norwegian, a young man of 22 traveling on a meager state scholarship. The pamphlet's title made an audacious, almost unbelievable claim, a demonstration of the impossibility of solving the general algebraic equation of the fifth degree. For over 2.5 centuries, the search for such a solution, a formula involving only the coefficients of the equation, standard arithmetic, and the extraction of roots, had been a kind of holy grail for algebraists. The greatest minds from Lagrange to Euler had grappled with it and failed. And now, this obscure student from the continent's northern periphery declared the quest itself to be a phantom. The initial reception was one of polite dismissal, even suspicion. The work was so compressed, its reasoning so economical, that it was difficult to follow. When a copy allegedly reached the desk of the formidable Carl Friedrich Gauss in Göttingen, the prince of mathematicians is said to have set it aside without serious examination, perhaps assuming it was another piece of crank literature from a hopeful amateur. The pamphlet's very brevity worked against it, suggesting a lack of depth, where in reality there was an almost terrifying profundity. This was the world's first encounter with Niels Henrik Abel, a mind of the first rank arriving on the scene, with a discovery that would fundamentally alter the landscape of mathematics, yet finding the world unprepared to listen. The story of his life is one of the most brilliant and tragic in the annals of science, a condensed epic of transcendent intellectual achievement, played out against a backdrop of relentless poverty and professional neglect. Abel's origins offered few clues to his eventual destiny. He was born in 1802 in Finland, Norway, a nation that was then culturally and scientifically distant from the European core of France and Germany. His father was a Lutheran pastor and a prominent political figure, a man of intellect and education who helped shape Norway's first constitution. This environment provided the young Abel with an initial exposure to learning. The family's fortunes, however, were precarious. His father's political career ended in controversy, and he succumbed to alcoholism, dying when Niels was 18. This event plunged the family, already struggling, into a state of near destitution that would haunt Abel for the remainder of his short life. The responsibility for supporting his mother and 6 younger siblings fell heavily upon his shoulders, a burden that would shadow his every intellectual pursuit. His salvation and the world's came in the form of a teacher. After a miserable experience under a brutal instructor at the cathedral school in Christiania, the city now called Oslo, Abel and his brother came under the tutelage of Bernt Michael Hombo. Hombo was a gifted mathematician himself, and he immediately recognized that in the quiet, unassuming Abel, he was confronting a prodigy of historic proportions. He famously declared that Abel's genius was of such a caliber that it was a privilege to witness. Hombo abandoned the standard curriculum for his star pupil. Instead, he handed Abel the masterworks of the mathematical canon, the writings of Newton, Euler, Lagrange, and Laplace. Abel devoured them. With an astonishing acuity, he worked his way through their complex arguments, mastering their techniques, and quite remarkably, beginning to identify logical gaps and unstated assumptions in their proofs. He was cultivating a standard of rigor that was, at the time, exceptionally rare. While the giants of the 18th century had built powerful and beautiful mathematical structures, they often did so with an intuitive flair that left the logical foundation somewhat insecure. Abel, from his cold room in Christiania, was already thinking like a modern mathematician, demanding absolute precision in every step of a deduction. Abel became his fiercest advocate, championing his cause at the newly established University of Christiania and tirelessly petitioning the government to provide the young genius with the financial means to continue his work. The mathematical world Abel was preparing to enter was one of profound transition. The freewheeling, results-oriented spirit of the previous century was giving way to a new era of foundational questioning. In Paris, Augustin Louis Cauchy was laboriously laying the groundwork for modern analysis, providing rigorous definitions for limits, continuity, and convergence that would underpin calculus for all time to come. The intuitive understanding of a function was being replaced by a more abstract and powerful conception. This demand for rigor was transforming analysis. Meanwhile, algebra was dominated by the imposing shadow of the general polynomial equation. The formula for solving quadratic equations of the form x squared plus bx plus c equals 0 had been known since antiquity. In the 16th century, Italian mathematicians had produced spectacular complex formulas for the cubic and the quartic, equations of the third and fourth degree. It seemed a matter of course that a similar formula must exist for the quintic, the equation of the fifth degree. Yet it remained stubbornly elusive. The problem became a benchmark of mathematical prowess, a challenge that drew in generation after generation of the finest intellects. Joseph Louis Lagrange, in a monumental paper from 1770, had conducted the most thorough analysis to date. He examined the known solutions for the lower degree equations and discovered a unifying principle involving permutations of the roots. His method, however, failed when applied to the quintic, leading him to suspect that a solution of the kind sought might be impossible. This suspicion, however, remained an unproven conjecture. This was the grand challenge that captured Abel's imagination. Even before his European tour, he believed he had found the coveted solution. He submitted a paper to the Danish mathematician Ferdinand Degen, who, while impressed, wisely asked Abel to provide a concrete numerical example of his method. In the process of working one out, Abel discovered a fatal error in his own logic. The experience was formative. It tempered his youthful ambition with a deep-seated intellectual integrity. He returned to the problem with a new perspective. His goal was altered from finding a formula to investigating the very possibility of its existence. The result of this deeper inquiry was the 6-page pamphlet he carried with him to Germany. Its message was revolutionary. The search was over because the treasure could never be found. For a young man living on borrowed money, whose future depended entirely on the impression he made upon the mathematical elite, this was an extraordinary gamble. He was introducing himself to the world with a proof of a negative, a demonstration of a boundary. He was showing where mathematics could go by defining a frontier it could forever approach but never cross. That 6-page pamphlet contained the culmination of this profound intellectual shift. It was a document whose conclusion was a statement of profound limitation, an elegantly reasoned argument for impossibility. For centuries, the greatest minds in mathematics had sought a general formula for the roots of the quintic equation, a polynomial of the fifth degree. The quest was a natural extension of a triumphant history. The solution to the second-degree quadratic equation was known to the ancient Babylonians. In the 16th century, a flurry of brilliant and often contentious work by Italian mathematicians, including Scipione del Ferro, Niccolò Fontana Tartaglia, and Gerolamo Cardano, had yielded the general solution for the cubic or third-degree equation. Cardano's own student, Lodovico Ferrari, quickly followed with a method for solving the quartic, the equation of the fourth degree. These solutions were all of a particular type. They were algebraic, meaning they expressed the roots of the polynomial using only its coefficients combined through a finite sequence of arithmetic operations, addition, subtraction, multiplication, division, and the extraction of roots, or radicals. The formulas were often monstrously complex, yet they existed. They were universal keys that could unlock any equation of their respective degrees. For 2.5 centuries following Ferrari's discovery, mathematicians labored under the powerful assumption that the quintic would eventually yield in the same way. The problem was one of ingenuity. The formula was presumed to be hiding, awaiting a mind clever enough to uncover it. The great Lagrange, in his sweeping 1770 analysis, came closest to understanding the underlying structure. He studied the permutations of the roots and saw why the methods for the cubic and quartic worked, yet the path to the quintic remained shrouded in fog. He had illuminated the landscape without revealing the final destination. The first serious claim that the destination was a mirage came from the Italian physician and mathematician Paolo Ruffini in 1799. Ruffini published a 500-page book attempting to prove the general quintic's insolvability by radicals. His work was pioneering. He correctly identified the essential role of the group of permutations of the roots and intuited many of the properties that would become central to the complete theory. His argument, however, was sprawling, obscure, and contained gaps that his contemporaries found unbridgeable. The mathematical tools of the day were insufficient to formalize his insights with the rigor the community demanded. Lagrange himself, upon reviewing the work, expressed skepticism, and without his endorsement, Ruffini's proof was largely dismissed, a fascinating but ultimately unconvincing effort. Abel's proof was different. It possessed a crystalline clarity and an unassailable logical force that Ruffini's lacked. He began by assuming that such a general formula, built from radicals, did exist. He then meticulously analyzed the algebraic properties that such a formula would have to obey. A solution by radicals implies a specific structure, a hierarchy of field extensions where each new field is created by adjoining the root of something from the previous field. Abel demonstrated that any such expression, when viewed as a function of the polynomial's coefficients, must have a certain structural symmetry. He then turned to the general quintic equation itself. He showed, through a brilliant analysis of the permutations of its 5 roots, that the symmetry group governing the quintic, what we now call the symmetric group on 5 elements, Siv 5, is fundamentally incompatible with the hierarchical symmetry imposed by a solution in radicals. The structure of the problem is richer and more complex than the structure of the proposed solution. The key, which he later articulated with greater clarity, is that the group S5 contains a simple subgroup that prevents it from being broken down in the step-by-step manner that solvability by radicals requires. He had discovered a fundamental mismatch between the object and the tool. The lock was of a design that the key of radicals could never turn. Armed with this monumental discovery, self-published at his own expense, Abel embarked on his European tour in 1825. His first major stop was Berlin, a city of rising mathematical importance. There, he had the great fortune to meet August Leopold Krell, an engineering official and passionate mathematical amateur who was immediately struck by Abel's genius. Krell was so impressed that he decided to found a new mathematical journal, the Journal für die Rein- und Angewandte Mathematik, or Krell's Journal, which would become one of the leading mathematical publications of the 19th century. Its very first volume would be dominated by Abel's papers, cementing a lifelong friendship and providing Abel with a vital outlet for his work. From the encouragement of Berlin, Abel traveled to Paris in 1826, the undisputed center of the mathematical universe. This was the city of Lagrange, Laplace, Legendre, and reigning supreme, Augustin Louis Cauchy. Here Abel hoped to finally receive the recognition his work deserved. He spent his meager funds preparing a far more comprehensive and polished version of his impossibility proof, a masterpiece he titled Mémoire sur une propriété générale d'une classe très étendue de fonctions transcendentes. This memoir contained what is now known as Abel's theorem, a vast generalization of results on elliptic integrals that was even more profound than his work on the quintic. He submitted it to the French Academy of Sciences, the highest authority in European science. The Academy assigned 2 referees to evaluate the paper, Adrien-Marie Legendre and Cauchy. Legendre, by then an old man, pleaded that the manuscript's handwriting was difficult to read. The primary responsibility fell to Cauchy. What happened next is a moment of quiet tragedy in the history of science. Cauchy was a mathematician of immense power and prolificacy, but he was also notoriously overworked, disorganized, and often dismissive of work by younger, unknown mathematicians. The memoir, a work that would shape the future of algebra and analysis, was apparently taken home by Cauchy, who then either set it aside and forgot it, or lost it amidst the towering stacks of his own papers. Abel waited for months in Paris, his financial situation becoming desperate, his health beginning to fail from the tuberculosis that would eventually claim his life. He heard nothing. The verdict from the world's leading mathematical body was silence. The greatest triumph of his young life, the definitive solution to a problem that had occupied the finest minds for over 250 years, lay unread and unacknowledged on a shelf or in a drawer. The indifference was a devastating blow. Dejected and impoverished, Abel left Paris, his groundbreaking work effectively buried alive. His mathematical mind, however, continued to burn brightly, turning its attention toward other deep problems whose solutions would secure his immortality, even as his own time was running out. With the Parisian chapter of his life closed in disappointment, Abel's intellectual energies sought a new and equally formidable challenge. His mind, a crucible of abstract thought, turned toward a class of mathematical objects that had resisted the efforts of the world's finest analysts for nearly a century, the elliptic integrals. These were the strange, stubborn integrals that arose when one attempted to calculate the arc length of an ellipse, a seemingly elementary problem with a deceptively deep structure. For decades, the great Adrien-Marie Legendre had dedicated himself to their study, meticulously cataloguing their properties and creating vast tables of their values. He had built a magnificent edifice of special cases and relations, yet the central mystery remained. The integrals themselves, expressions like the integral of a rational function involving the square root of a cubic or quartic polynomial, defied expression in terms of the familiar elementary functions, the polynomials, logarithms and trigonometric functions that formed the analyst's toolkit. The central difficulty lay in the problem of inversion. For the simpler circular functions, the relationship was clear. The arcsine function, for instance, arises as the inverse of an integral used to calculate the arc length of a circle. If one defines a length u as the integral from 0 to x of 1 divided by the square root of 1 minus t squared dt, then the inverse relationship x equals sine of u gives birth to the entire field of trigonometry. The question that haunted Legendre and his contemporaries was profound. What new world of functions would be revealed if one could successfully invert the elliptic integrals? What kind of function, let us call it paved, would satisfy the relationship x equals paved of u, where u is the value of an elliptic integral? Legendre wrestled with this question, but the answer remained elusive, hidden behind a wall of computational complexity. Abel's approach was a stroke of genius born from a complete reorientation of the problem. He shifted the entire focus of the inquiry. The community had been fixated on the integral, US Abel fixed his gaze upon its inverse, the function phi of US. He decided to treat this unknown function as the primary object of study and to deduce its properties directly. This conceptual leap was transformative. His first move was to do what he had done with algebraic equations, to consider the variables as inhabitants of the complex plane. By allowing the argument u to take on complex values, he unlocked a hidden world of structure that was completely invisible when restricted to the real number line. What he found was astonishing, a discovery that would forever alter the landscape of analysis. The familiar trigonometric functions like sine and cosine possess a single period. The value of sine of x repeats every 2 pi units along the real axis. Abel's new elliptic functions, when viewed in the complex plane, revealed something far more intricate and beautiful. They possessed two distinct periods, a fundamental period omega-1 and a second period omega-2, such that the ratio of omega-1 to omega-2 is a non-real number. This meant the function phi of u would return to the same value when u was increased by omega-1, and also when u was increased by omega-2. The function repeated its values over a lattice of points, a grid of parallelograms tiling the entire complex plane. This property, known as double periodicity, was entirely new. It was the fundamental defining characteristic of this new class of functions. Abel had discovered a new continent in the world of mathematics, populated by functions whose rich geometric structure had been completely unsuspected. The implications were immediate and profound. The theory of doubly periodic functions became a cornerstone of 19th-century mathematics, forming the foundation of complex analysis alongside the work of Cauchy and later Riemann and Weierstrass. These elliptic functions provided explicit solutions to a vast array of problems in mechanics, geometry, and number theory, from the motion of a pendulum to counting the number of ways an integer can be written as a sum of 4 squares. Abel's insight had turned a collection of intractable integrals into a powerful and elegant new theory. His ambition, however, was boundless. His mind constantly sought the most general possible formulation of any idea. The elliptic integrals involved the square root of a polynomial of degree 3 or 4. Abel proceeded to investigate the integrals of algebraic functions in their full generality. He considered integrals of the form, the integral of r of x, y dx, where y is an algebraic function of x, defined implicitly by any polynomial equation, p of x, y equals 0. These more general objects are now known as Abelian integrals, a name that forever links him to this vast and fertile field of study. They represent the natural generalization of logarithmic, trigonometric, and elliptic integrals. Within this grand framework, he proved a result of breathtaking power and scope, now known as Abel's theorem. This theorem provides a massive generalization of an addition formula for elliptic integrals first found by Euler. Abel's theorem establishes a fundamental relationship for a sum of any number of Abelian integrals taken along an algebraic curve. It states that a sum of such integrals can be expressed in terms of a fixed number of similar integrals, a number determined by the genus or complexity of the underlying algebraic curve, plus a term composed of algebraic and logarithmic functions. This theorem forges a deep and profound connection between the geometry of the curve, defined by its polynomial equation, and the analytical properties of the integrals defined upon it. It was one of the first truly deep results in what would become algebraic geometry, providing the essential key that would later allow Bernhard Riemann to develop his own theory of Riemann surfaces. In the depths of his poverty and illness, working with a clarity that defied his circumstances, Abel had laid the foundations for entire new branches of mathematics, creating tools and concepts that would occupy mathematicians for the next century and beyond. The same creative impulse that forged new connections between geometry and analysis also drove Abel to redefine the very standards of logical proof within mathematics. His intellectual gaze extended across the entire landscape of analysis, identifying areas where intuition had outpaced certainty. He perceived a structural weakness in the edifice of calculus, particularly in the widespread and often reckless manipulation of infinite series. During the 18th century, mathematicians of even the highest caliber, including the great Leonhard Euler, handled these infinite sums with an audacious formalism, rearranging terms and substituting values with a confidence that lacked a secure logical footing. This approach yielded a trove of spectacular results, yet it also produced paradoxes and contradictions that hinted at a deep, unresolved problem at the heart of the discipline. Abel confronted this ambiguity with an unwavering demand for rigor. He was a principal architect of the new analytical ethos that would come to characterize 19th-century mathematics. His 1826 paper on the binomial series stands as a monument to this new spirit. The series, which expresses the quantity open parenthesis 1 plus x close parenthesis to the power of z as an infinite sum, had been used for over a century, yet a complete and correct proof of its convergence for arbitrary complex exponents was missing. Abel provided it. With meticulous care, he established the precise conditions under which the series converges to its intended value, thereby placing one of the most useful tools of analysis on an unshakable foundation. His work on series introduced what is now known as Abel's test for convergence, a powerful criterion for determining the behavior of series of the form the summation of a sub n times b sub n. His theorem on the product of two series, now called Abel's theorem, provided a rigorous justification for their multiplication. These contributions were more than solutions. They were statements of principle, demonstrating that clarity and absolute proof were the essential virtues of the mathematical arts. This quest for foundational certainty led him into other novel territories. While investigating the classic tautochrony problem, the challenge of finding the shape of a curve such that an object sliding on it takes the same amount of time to reach the bottom, regardless of its starting point. Abel formulated an equation of a type rarely seen before. The unknown function appeared under an integral sign. He had formulated what is now called an Abel integral equation. His ingenious method for solving it was one of the very first triumphs in the theory of integral equations, a field that would later become indispensable in areas ranging from quantum mechanics to signal processing. In each endeavor, from group theory to elliptic functions and the foundations of analysis, Abel's work possessed a characteristic depth, revealing the hidden structures that governed the mathematical universe. The profound originality of these ideas, however, contributed to their initial neglect. Recognition eluded him during his lifetime, a consequence of a confluence of unfortunate circumstances. His geographic isolation in Norway placed him far from the intellectual centers of Paris and Berlin. His persistent poverty was a practical barrier, making it difficult to travel, to network with established figures, and to disseminate his work through expensive academic publications. The most infamous episode remains the mishandling of his Paris manuscript on transcendental functions. Submitted to the French Academy of Sciences in 1826, this magnum opus, which contained his monumental theorem on abelian integrals, was given to Augustin Louis Cauchy for review. Cauchy, a brilliant yet notoriously disorganized mathematician, apparently misplaced it. The paper, a work that would have immediately established Abel as a leading light of his generation, languished unseen for years. Its loss was a source of profound despair for Abel and a staggering loss for the mathematical community. His genius was ultimately too powerful to remain hidden forever. After his death, the true scale of his achievements began to emerge, thanks in large part to the tireless advocacy of August Krell, who continued to publish Abel's papers in his journal. Mathematicians across Europe started to grapple with his dense and revolutionary manuscripts. Carl Gustav Jacob A., his great contemporary and rival in the development of elliptic functions, was instrumental in building his posthumous reputation. Upon learning of a new result by Abel, Jacob A. famously declared that Abel had left the mathematical world with enough work to keep it occupied for 500 years. This was a generous and accurate assessment. Slowly, the lost Paris manuscript was rediscovered and finally published by the French Academy in 1841, a full 15 years after its submission and 12 years after its author's death. It was a moment of supreme tragic irony, a final, resounding confirmation of a genius who had long since departed. The legacy Abel constructed in his few productive years is astonishing in both its breadth and its depth. The concepts he introduced have become part of the very fabric of modern mathematics. The abstract idea of a group, which he distilled from the study of permutations of roots, is today a fundamental organizing principle in algebra, physics, and chemistry. His insistence on rigor permanently transformed the field of analysis, setting the standard for all subsequent work. The theory of elliptic and abelian functions, which he pioneered, blossomed into vast areas of complex analysis and algebraic geometry, leading directly to Bernhard Riemann's theory of Riemann surfaces and the complex manifolds that are central to modern theoretical physics. He was an architect of new worlds, a thinker whose ideas possessed a generative power that continues to unfold. In 2002, the government of Norway created a fitting tribute to its most celebrated scientific mind. The Abel Prize, awarded annually for outstanding contributions to mathematics, stands as one of the discipline's highest honors, often equated in prestige to the Nobel Prize. The establishment of this award provides a poignant counterpoint to the narrative of his life. The man who struggled in obscurity and died in poverty is now the namesake for one of the world's most significant and lucrative academic awards. The prize is a permanent global acknowledgement of his monumental stature, a correction of the historical record written on a global scale. In the final analysis, Niels Henrik Abel represents the purest form of intellectual creation under the most severe of pressures. His life story is a stark reminder of the fragile relationship between genius and circumstance, yet his intellectual legacy is one of triumphant and enduring power. He fundamentally altered the character of mathematics, guiding it away from computational virtuosity and toward a deeper exploration of structure, system, and logical certainty. His work resonates through the centuries, embedded in the equations of engineers, the theories of physicists, and the abstract structures explored by pure mathematicians. In the pantheon of great mathematical minds, Abel occupies a unique and exalted place. His was a brief and brilliant flame, but it cast a light that illuminated the path for generations, forever changing the landscape of human thought.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.